Hello, good evening, everyone.
Good evening, ma'am.
Yeah. So today we'll do solve with this for week 2. Before we proceed, any doubt you have in week 2? No doubts? All right. So we'll start with the solve with this session. So we'll do some 8 problems over here, and
I have a question, if I can ask.
yeah.
It is regarding the graded assignment of week 2.
Mhm.
I'm not asking the solution for the question, but one of the question involves X transpose X. And I want to know whether this X transpose X is any matrix, X is any matrix, or it is a specific matrix, like it's a matrix of centralized data set or not. That's what I wanted to ask. Because that has not been specified in the question.
Okay. Can you tell me the question number?
Just a minute. I'll just tell you the question number. Yes, it is question number 4.
Okay. Here you're asking whether my data set is centered or not.
Yes, this X matrix which we are talking about here in this question, whether this matrix is a centralized matrix or it is any X matrix.
It is any X matrix.
Okay.
Yeah, it cannot be centralized.
Okay, because here we are always talking about centralized matrix. No, that is the reason why
Yeah, but the question here is quite different. You have a matrix K given to you, and you have to decide which can be the good choices for this special matrix K.
Okay, that clears my doubt. Okay.
Yeah. All right. So week 2 deadline is today, if you all know. All right. So here we have the first question, but we'll do this question at the end. So this is the again topic for this week. So the very first question that we will do is for the kernel. So what is given to us is kernel is defined for R2 cross R2 to R, and this mapping is given as X transpose Y ka square. Okay. Now, if both X and Y is in 2 dimension, so let's say X is my X1 comma X2 and Y is my Y1 comma Y2, then which you have 4 transformations given to you over here. So which of the following file will correspond to your K, will correspond to the kernel K?
Fourth one.
Fourth one. Anyone else? So that said it's
The fourth one. Fourth one is correct.
fourth one is correct. Okay. So is this clear to all of you why the fourth one is correct?
Yeah, it's clear. We can write it as phi of X transpose phi X.
Yeah. Okay. So yeah, so the kernel matrix is given to us. We know our X and Y, and we can just work on this, and we'll get the like finally k of xy, we will be able to write it as this form. So we can call this as phi of x, and this is phi of say y. So this is more of the form phi x transpose phi x. So that's why option 4 is correct. I hope this is pretty straightforward. I hope nobody has any problem. All right. Let's move to the third question. So here you have a kernel function defined to you from R cross R to R, and it is given to us as k of x1 comma x2 is equal to x1 x2 plus x1 squared x2 squared plus x1 cube x2 plus 1. So the question is, can we call this a valid kernel?
No, man.
No.
X1 is a cube here, and the third term x1 is a cube, whereas x2 is
Also,
not
it
a
is not
cube.
symmetric. It is also not symmetric.
Yes, it is not symmetric, right? We know that for a map, for a kernel to be valid, valid mapping, this should be symmetric, and also it should be positive semi-definite matrix, right? So the mapping that is given to us here, it is not even symmetric. So the first condition only, it's not satisfied. So we can say that this is not a valid kernel. All right. So this is right. Okay. So here you have two different kernel given to you. One is our Gaussian kernel and the other is our polynomial kernel. So the Gaussian kernel is given by K1, which is e to the power minus of norm of x minus y whole square. And a polynomial kernel is given by K2, which is x transpose y plus 1 whole cube. This is of degree 3. Now, if we define a new kernel function, and this we are able to define because since K1 and K2 are both a valid kernel, so we can do this, or just K1 plus 3K2, and this is a new kernel that we have defined. Now, based on this kernel, the question is, if you are given this data set, so where my x1 is 1 comma 2, x2 is minus 1 comma 2, x3 is 1 comma minus 2, and x4 is minus 1 minus 2. So if this is the data set that is given to us, can you find the kernel matrix is the question. So how do you find the kernel matrix?
We have to apply the kernel function to each of the data points.
We have to, okay, yeah. So we have 4 data set, right?
So to x1 and x1 x2 and so on.
Yeah, so it will be a 4 cross 4 matrix. So this will be a 4 cross 4 matrix, and here it will be this is basically K11, K12, K13, K14, so on it will go, right? So now if we look at K11, so basically K11 is K of x1 comma x1, right? So now what is the kernel matrix given to us? This is the kernel matrix given to us. So what we are saying is we want K1 of x1 comma x1 plus 3 times K2 of x1 comma x1, right? Now how is K1 defined? K1 is defined as e to the power minus of norm of x minus norm of y square. So this is just going to be e to the power
1.
minus of, yeah.
E
So
to the power
x1,
0. E to the power 0.
yeah, e to the power 0, right? Okay. What about the second term?
6 cube.
6 to
6 cube.
6 cube.
6 cube. Yes.
Q6 cube.
Okay. So all right. So this is how we can find each of the entries, like for this 4x4 matrix, and that will give us the kernel matrix for this data set. So when we do the whole calculation, what we get here is for the very first term, you get 649. So similarly, you can find it for every other entry, and the final kernel matrix that you get should be this. So such kind of like so much calculation in a question will not come, of course, in the exam, but this is just to show like how can you find a kernel matrix for any problem, like given any data set, how can you find the kernel matrix? This is just to demonstrate that, because such it's a lot of calculation to calculate this 4x4 matrix, and in any exam it won't be asked from you, right? But you should know how to.
3 cross 3 or 2 cross 2?
Sorry.
In exam, 3 cross 3 or 2 cross 2, which will be asked in general?
That, I mean, max 3x3, no, never 4x4. I mean, you will not be asked to compute everything over there. This was just to demonstrate how can you find the kernel matrix. Okay. So I hope all of you know how can you find the kernel matrix. So every term in this matrix, so this is basically what it is saying is, this is my k of x1 comma x1. This is saying is that this is my k of x1 comma x2, right? And if I look at, let's say I look at this, so this is in the second row, this is basically k of x2 comma x4, right? Similarly, if I look at this entry, this is basically k of x4 comma x3. So this is what all the entries in this matrix represent. And we already knew that my kernel matrix, my kernel function is this, right? So we can just work on that, and we should be able to compute each and every entry in this matrix. I hope that is clear to everyone. Okay. Let's go to the fifth question. So here you have n data points, and it is given to us that the mean of the data point is 0. Now we are taking a another matrix P, which is a 3x3 matrix, and each of the entry in this matrix, which is Pij, is denoted as Xi transpose Xj. Okay. So if each of the entry is Xi transpose Xj, the first question that is asked is how many data points are there in this setup?
3.
3. Is it clear to all of you why it is 3?
Yes, ma'am. It is 3 by 3 matrix. So should be 3 data points and 3 features.
Okay, correct. So there are total of 3 data points over here. So that's the answer. Now, the second question that is asked is, now let's say for this matrix P, which is 3x3 matrix. So for this matrix, you will have 3 eigenvalues basically, right? And the eigenvalues that are given to us is, let's say, L1, L2, and L3. And they're in this order, where L1 is the largest eigenvalue, L2 is the second largest eigenvalue, and L3 is the third largest eigenvalue. And one more condition is given to us, that all of these eigenvalues are positive, right? So all these eigenvalues are positive, and this is the like L1 is greater than L2, L2 is greater than L3, and so on. Now, if this is the case, then what can you say about the trace of the covariance matrix? What is the trace of the covariance matrix?
Second option, I think.
Second option. Okay. So first of all, what is the covariance matrix? What is C?
1 by n x
XX transpose, XX
1
transpose,
by
and
n XX transpose, right? So the eigenvalue that are given to us are for the matrix X transpose X, right? And we know that all the non-zero eigenvalues for X transpose X and for the matrix XX transpose will be equal, right? So if I know the eigenvalues of the matrix X transpose X, which is L1, L2, and L3, then I also know what is the eigenvalues of the matrix XX transpose. So that will also be L1, L2, and L3. All right. So if these are the eigenvalues of of the matrix XX transpose, then the eigenvalue, and if I call this let's say as A, then the eigenvalues for the matrix XX transpose divided by n, which is my covariance matrix, this would be just L1 divided by n, L2 divided by n, and L3 divided by n, right? So these are the eigenvalues for my covariance matrix. Now the question is asked is, what is the trace of the covariance matrix? And we know that the trace of the covariance matrix is just the sum of the all the eigenvalues, right? This is what we know. So we'll just the answer would be option E over here. I hope this is clear.
Yeah, basically.
Excuse
Okay.
me.
Yeah.
Here in P ij equals to small x, what does the small x transpose mean? Because x transpose x is like a matrix formation. It is understandable, but small x, what does it mean?
This is each of the data point, right? This is let's say if I have total of 3 data point in this question, right? So I have something like x1, small x1, small x2, small x3, right? So each of the entries of this P, we give it as xi transpose xj, right? This is we have seen this in lecture also, like how this derivation and everything has come up.
Okay.
So this is basically the dot product of any two data point.
Okay.
Okay. Now, once we know what are the eigenvalues of the covariance matrix C, we are able to find the trace. Now, the third question that is asked is, if the eigenvalues of P are 15, 30, and 24, then find the variance along the second principal component.
24.
8, man.
It will be 8.
Man.
Okay, 8 and 24 is what? Which one is the final? I think most of the people said 8.
8.
Yes. So 8 is the answer for this question. Why not 24? Is because, first of all, we have to find here the variance along the second principal component. So it's obvious that we should take the second largest eigenvalue, right? But now we know that the covariance matrix C is XX transpose divided by n, and our eigenvalues will be L1 by n, L2 by n, and L3 by n. And these eigenvalues are for these are my L1, L2, L3, right? So if these are my L1, L2, L3, then in that case, for the covariance matrix, the eigenvalues are going to be, it's going to take the form of 15 divided by 3, which is 5, 30 divided by 3, which is 10, and 24 divided by 3, which is 8. Now, this is the eigenvalues. These are the eigenvalues for my covariance matrix. So if I have to find the variance along the second principal component, I will pick the second largest eigenvalue, and that is 8. So 8 is the answer. I hope it's clear to everyone.
Yeah, clear.
Okay. All right. So this is the sixth question. So the question says here, you have this is you have a data set where each of the element in the data set is coming from R2. Okay. So we are defining a kernel matrix, a kernel function, which is from R2 cross R2 to R. Now, this kernel is given in this form, which is k of x comma x dash is equal to x transpose x dash plus 1 whole square. This is the kernel that is defined. Now, every data point here, so using phi, which is a mapping from R2 to R6, we map every data point to R6. And the observation that we make is that my phi x transpose phi y is equal to k of xy. So we have the data set, we have our x's in R2, and we mapped this data point to a higher dimension, and this is phi of xi, which belong to R6. So from R2, the data point has been moved to or mapped to R6. Now, from this, the observation that is made is that my k of xy is nothing but phi of x transpose phi of xy. This is observation that we take. Now, every point in the mapped space is in the null space of vector u, where u is given by this vector, right? So this is my u. So the first question is, what could possibly be my phi of x? The first, that is my first question. What can be phi of x?
The six-dimensional vector, right? A square, B square, 1, root 2AB, root 2A, and root 2B.
Sorry, can you repeat?
If the vector is x equal to AB, if the
Okay.
vector is x equal to x1, x2, okay, it is x1, here
X1,
it
X2
is
is
given.
given.
So x1 square, x2 square is a six-dimensional vector. x1
Correct.
square, x2 square, 1 square root of x1, x2, square root 2 x1, and square root 2 x2.
Right.
That is the phi.
That is what can be defined as phi of x. Right. So, okay, I'll just go to the where it is done. Then I will also just tell what the second question is. You have to find the relationship between the features of every data point in R2. So what is the relationship that we find between the data point is what the next question is. So if we just look at the first question, so the kernel is defined in this way. The kernel is x transpose y plus 1 whole square. And once you solve for it, we all know how to do it. So this has been done in the class also. So x is taken as x1, x2, y is taken as y1, y2, and we can solve for this. And we can see that I can write my k of x1, k of x comma y as this, which is x1 square under root x1, x2 square under root x2, under root 2 x1, x2, comma 1. So this is what we can think of as my phi of x. Right? Now, the another information that was given is um, every data point in the map space is in the null space of the vector u, right? So what possibly is the statement saying? So this statement was what the statement is saying is that my phi x transpose times u should be equal to 0.
Zero, yes.
Yes.
So can you use this property, like can you use this phi x transpose u is equal to 0 and see what do you get?
I think it will be a circle.
Just try it out. And once you do this, you should be able to see the relationship between the features of the data point. I will just write the phi x here for so the phi x we have is x1 square under root 2 x1, x2 square under root 2 x2, under root 2 x1 x2 1. This is my phi x. Did anyone get anything?
Yeah, I got x1 minus h whole square by a square plus
X1 minus
h x1 minus h whole square
uh,
divided by a square
mhm,
plus y1 minus k whole square
mhm,
divided by b square
mhm.
equals 1.
Yes,
It's a ellipse, I think.
it's an
Yeah.
equation.
Yeah, it's an ellipse.
Yeah. So this is an equation of ellipse. So this is what so between the features of every data point, this is the relationship that we get. And this is basically
This will be equal to R, right? Not okay, one. Okay, yes, yes.
so all of you got this answer.
Yeah.
Yeah. Okay. All right. Let's move to the next question. Um, so here, all right, just show the solution part also. So this is just a theoretical question, and the question that is asked is you have n data points in RD, and we know that these quite large as compared to n. So we have seen this in our class also. This situation where my number of features is quite large as compared to number of data points. Now, if to find the principal component, if we use this algorithm, then can you find any error that is there in this algorithm is the question. So the very first step that it says is put every data point in the columns of a matrix and call it X. So there is no issue in that. I mean, this is how we all start. So every data point we put in the matrix and we call it X. This is fine. Now, the second step it says is that you find K to be XX transpose, right? And what is this XX transpose? This XX transpose is not the kernel matrix that we have seen. This is the covariance matrix.
Yes, but 1 by n should be there. That's the
Right. But this is, I mean, this K is not XX transpose. This K should be X transpose X. So given any data point, we have to like once we have the data set, we put it in the matrix X. Yeah. Then after we put it in the matrix X, we also center the data set. That should be our second step, to center the data set. Now, once we center our data set, we find the kernel matrix, which is X transpose X. And afterwards, once we find the kernel matrix, we find the eigenvalues for this kernel matrix of this X transpose X and their corresponding eigenvectors, right? So once we find these eigenvectors, then we can give the principal components for my covariance matrix, which is given by WK is equal to X times alpha K. From the lecture, I am taking these notations. Some X times alpha K. And what we had obtained is that this alpha K was nothing but beta K divided by under root of n lambda K, where beta K was the eigenvector for the matrix X transpose X, and n lambda K were the eigenvalues for the matrix X transpose X, right? So if that's the case, then in the fourth step, my ith principal component is not going to be xei divided by li. It should be my xei divided by under root of li, right? Because that's what we do. So these are the three major changes that we should make in this algorithm to make it right.
And once we center the data set, we are supposed to use the centered data set and not X for calculation of K, right?
Yes, center data set.
So it will be X centered. K will be X centered
Yeah.
transpose X.
Basically, it's X
KC.
centered. Yeah.
And the
I'll
I
just write it
principal
as
component
C.
will also be X centered EI by square root of Li.
Yeah, it's everything. You think of it as all the centered one. Yeah. Okay. Let's move to the next question. So here in this question, what is given to us is every data point, whatever data set we have, the data point follows or satisfies this equation. So this is again, this is the equation of a hyperbola basically. So my data point follows this expression, and there is a mapping that is given to us, which maps this kernel, this function file, which maps our data point from R2 to R6, and it is given as this, which is x1 square under root x1 x2 under root 2 x1 x1 square under 2 x2 and 1. So this is how phi x is defined. Now, and this is defined in such a way such that phi x transpose phi y is given by the polynomial kernel of degree 2. So I'll just write it here. This what is this? My polynomial kernel. So this polynomial kernel is my x transpose y plus 1 whole square. This is what we'll use. So what you have to find is a vector which is orthogonal to every data point in the map space. So this is your question. Find a vector which is orthogonal to every data point in the map space.
1 by a square 0 0 minus 1 by b square 0 and minus 1.
1 by a square
0 0 0
0 0, okay.
minus 1 by b
Minus
square
1 by b square
0
0
and minus 1.
minus 1, okay. Anyone else? Anyone else has the answer for this question? Is it clear to everyone what we have to find? No, yes. Okay,
Yeah, it's clear, ma'am.
it's clear.
Yeah, it's clear.
Okay, so all of you got this as the answer?
No, ma'am. Can you explain, ma'am?
Okay.
Orthogonal means that vector dot pi of x equal to 0.
Yeah.
Is it?
Yes.
So from that, how we find them? Ma'am? Can you solve?
Okay. So see, the phi x is given to us, and what is also given to us is this relationship, right? So you have to find a vector which is orthogonal to every data point in the map space. So what is from here? Can you look at this? So this you can write it as x1 square by a square minus x2 square by b square minus 1
Minus 1.
is equal to 0. Right? So this is what we can write. Now, if I take the dot product of, so just go down. So if we take the dot product of this phi of x times this vector, right? So how did we get this basically? We had this term, which is x1 square root 2 x1 x2 root 2 x1 x2 square under root 2 x2 1. This is what we had, right? And if we take the dot, this is my phi x, and if we take the dot product of this with my vector this, which is from here, right? So this can be written as this whole thing. This whole thing can be written as minus 1 by a square, right? And I know there is no x1, x2 term, so the second component I can write it as 0. Again, there is
1
no...
by a square, ma'am. 1 by a square.
Oh, sorry,
Not
1 by a
minus.
square. Correct. 1 by a square. Now, the second component is 0 because there is no under root x1, like x1, x2 term coming over here, right? So that is why this component is 0. Now again, there is no x1, so the third component will also be 0 for this vector. For x2 square, it will be minus 1 by b square, because when you multiply x2 square with minus 1 by b square, you get minus x2 square by b square, right? So that's how you get this term, right? Now again, there is no x2 term in this. So if there is no x2 term, it will be 0. And at the end, you have this minus 1 coming here. So that you will get by multiplying 1 with minus 1, right? So this is a vector that I should get to get the which will be orthogonal to every data point in this map space. So what is this vector that we obtained? So this u that we got is 1 by a square, 0, 0, minus 1 by b square, 0, minus 1. So this is the answer. Okay.
Ma'am, how it becomes 0, ma'am? If you multiply x1 square into that 1 by a square, x1 square by a square plus 0.
See, you have to look at this thing. You have to look at this.
Oh, it
So
will
basically,
be okay. We will use that. Okay.
yeah, this is the equation that your data point satisfy. All right. Let's move to the next question. I will go to the very first question. Yes.
I mean that question only, that hyperbola question.
Mhm.
There
Yeah.
there was some y1, y2 terms. I mean that x1, x2 was given in the form of y1, y2 as well. Why is that so?
X1, X2. Hold on. Which side? Which part of it?
Here. This can be written as follows.
No. This is this. My kernel. This is my kernel kxy, where x is x1, x2, and y is y1, y2.
Okay, but we are not required to multiply this, right? Because this is just a representation kind of thing for this question.
Yeah, not required. I'm not saying this is required. It's not required because everything is already given to you in the problem statement.
Ma'am, how it will be that x transpose y plus 1 whole square equal to that x1 square? How it is coming, ma'am?
Sorry, can you repeat?
K of
How is
K of x comma y equal to x1 square to root 2 x1 x2 root 2 x1. How it is coming?
See, how is it coming? See, you have kxy to be x transpose y plus 1, right?
Yeah.
And what is your x? X is x1, x2. So what is x transpose? X transpose is x1, x2 in the row form. What is y? You have y1, y2 plus 1 whole square. Okay. Now I solve the term which is inside the bracket. So what do I get? I get x1, y1 plus x2, y2 plus 1 whole square. Now you take the product. You take the product, what do you get?
A plus b plus a square plus b square plus
x1 square y1 square plus x2 square y2 square plus 1 plus 2ab, which is 2x1 y1 x2 y2 plus 2x2 y2 plus 2x1 y1.
Yeah.
Now we can so I will just write it here. So what we got is we got x1 square y1 square plus x2 square y2 square plus 1 plus 2x1 y1 x2 y2 plus 2x2 y2 plus 2x1 y1. Now we can write it separately as in like a product of two vectors. So all the x term, all the x terms, I will write it in one vector. All the y term, I'll write in the second vector. So all the x1 square, then x2 square, then what I can take is 1. Then my 2 under root of 2 x1 x2 under root of 2 x2 and under root of 2 x1, and this can be like you can take the dot product of this with
V1 square,
y1 square
y2
y2 square
1.
1 under root of 2 y1 y2,
Yeah.
then under root of 2 y2 and under root of 2 y1, and that's how you get this.
But it is rearranged, no? Here that the column matrix. Yeah, right side. Yeah,
This one, right?
yeah. Rearranged, I think.
It is a little rearranged. I mean, you can take, it depends on how you have computed the sum.
Okay, okay.
Yeah, it depends on that.
Okay, understood, ma'am. Thank you.
Yeah, but this was already given to you here. Okay. All right.
This kernel is a general formula or
Which one?
kernel of uh, kernel we
This?
represent no k of x comma y. Is it formula general formula for
Uh,
kernel of degree 2?
I mean, you can also have x transpose y whole square. That is also fine.
So how we take polynomial kernel of degree 2 for this problem?
It is given to you in this question. I mean, this is obtained using the polynomial kernel of degree 2. You don't have to know what is used here, but just to show you how have we obtained this files, we can compute this and check.
Okay, okay.
Yeah.
Ma'am, degree 1 means power 1 will come.
Power 1 will come.
Degree 5 means 5 will come.
Yes.
Okay, thank you.
Okay. Now let's go back to our first question that we had left. Okay. This is a kernel matrix that is given to us, which is capital K. And for this kernel matrix, what you have to do is to find the centered kernel matrix. So you have to find K of C is what we can denote it as. How can we do this? So one hint that is given to you over here is like if you have any matrix, any D cross N matrix, then this is how you can get the mean vector for that matrix, right? And this basically, the one which you see here is a vector basically, okay? And it's a vector of order n where all the entries are 1.
We will treat this as some matrix, like a matrix of all the means, say I, and then we will do k minus ki minus ik and minus iki. So taking the j, I components and the square part of it. We'll subtract that.
Can you repeat what you said?
K minus ik minus ki minus iki.
K minus ik.
Ik?
What is ik?
I would be a matrix with only I components or j components like that.
Okay, you're saying like this?
Yeah, we can say that. No, but it's not needed because we'll do matrix multiplication. So yeah, it will do that. Yeah, so ik minus
Okay, we'll see this question. So okay. So to center any data set, what do we do? To center any data set, we subtract the mean vector for every data point, right? So this is basically what we perform, which is you take the data matrix that is given to you, and from there I will subtract this, which is 1 upon n, and each of the basically my 1 n cross n is it's all the entries are 1 here, and we're just dividing it by n, right? And this is basically gives us if you solve for this will basically give us the mean vector. Okay.
It's one.
This 1 n cross n is what is written here is basically 1 upon n, 1 1 1. It's all 1, and this is an n cross n matrix is what we are talking about.
X is D cross N, right?
X is D cross n here. So now if you do this, I know this is one way we can center this data set. But in our question, what is given to us is the kernel matrix, which is K. And K is given by phi x transpose phi of x, right? So my K is given by phi x transpose phi of x. So for this, again, we can use the same technique. So like if we have to like center, if we have to center x, what we did is we subtracted x from x, this matrix, what will be defined. So if we have to do the centered matrix for phi of x, this is what we will do, right? So now if you have the kernel matrix, which is phi x transpose phi of x, so to center this, this is what you will, this is what we will get here. So you subtract phi of x minus phi of x, one on this matrix I basically I transpose, and this is what, and once we solve it at the end, this is my final expression. Okay, this is my final expression, and I know the very first component, very first term here is my k, and k we already know. This component is again k, that we can put it over here, and all this are k. So we already know what the kernel matrix is, and we just have to multiply left hand side or right hand side by this one matrix, this I matrix. So can you just compute for this matrix K, what will you get the kernel centered kernel matrix? So the kernel matrix that is given to you is 1.8.5 is 1.8.5 0.8185 6.61. This is what is K given to us.
So I have computed it.
Okay.
Is it minus 10.4, minus 10.7, and minus 10.7 on the rows, and then second
Can you repeat? Minus
10.4, minus 10.7
Is it on the row side or
on the rows.
minus 10.7?
7.
Okay.
Then again minus 10.7.
Okay.
Then minus 10.7 in the, yeah, there. Minus 10.6.
Okay.
Minus 10.7.
Yes.
Then minus 10.7. Minus 10.7. And then minus 10.
Is this what we get?
Yes, I have done this. So maybe if I not made any mistake, then
Okay. Now, anyone else can tell me what do you get here?
Yes, I'm getting the same answer if in NumPy also.
You're getting the same answer.
Yes.
I'm sorry, ma'am. Actually, I made a mistake. I subtracted minus 1k1 instead of adding.
Okay. I don't think this is a correct answer.
Yeah.
Okay. So K
It won't
is
come in minus. It won't come in minus. That's what I was wondering.
so see, the kernel matrix is this, which is
Yeah, it's coming 3.2, 2.9, 2.9. Everything, yeah.
here 2.9.
Yeah, 2.9 in all the columns. Only the diagonals are 3.2, 3, and 3.6.
Okay, this also is not looking right. Okay. See, tell me what will you get for this? I think you're missing out n over here. One, this is not just all the entries as one, but you also have to divide it by 3. So for the very first, I mean, we already know this. So the second calculation when we do, which is 1.8.5 and 0.8, 1.6, 0.5.61. And this is 1 by 3, 1, 1, 1, 1, 1, 1, 1, 1, 1, right? So you just have to multiply everything, right? And this is 0.76 is what we get. Then again here you get 0.76. Again here you get 0.76. Then here you get 0.8, 0.6, 1.4, 2.4. Here it's all 2.4, 2.4, 2.4. And I think here you get something you just, and this
2.1,
here.
2.1, 2.1.
Yeah. So this is what after dividing it by 3. Sorry, this is 2.3 basically. 0.3. So this is what you should get. All of you getting this?
How did it become 0.76?
Because you missed to divide it by 3. How is my 1 n cross n matrix defined? It is defined as 1 by 3, 1, 1, 1, 1, 1, 1, 1, 1, 1. And that's how you're getting a wrong answer.
Wait a minute. Yeah, so now I'm getting the same answer. Yeah.
Yeah, you're getting this answer, right?
Yes.
So even in the lecture, one formula is given to compute this kernel matrix, like how to compute the centered kernel matrix. So even using that, you will get the answer. Basically the same thing it is. So you have Kij's C to be equal to K. You take the Kij, then you subtract it by theta I, indicator of J transpose minus indicator 1, sorry, I, theta J transpose plus a matrix P, I and J transpose. Okay. And the way theta we define, theta I to be defined, it is 1 upon n sum over Ki, let's say some small k, where small k will vary from 1 to n for all k. This for, sorry, for all j, j or, yeah, j. And, sorry, we have used I, right? For all I. And what P is my 1 upon n square sum over Kij for all I. So basically P is you just add all the entries in the kernel matrix and divide it by n square. So divided by 9, that should give you P. And what this means is on this ith element, you are going to put the value as 1, else you'll put 0. So whatever the ith entry is, I will put it as 1, or let's write it as transpose. So this will be maybe 0, 0. Let's say at the ith entry it is 1, and again 0, 0, 0. So this is the ith entry. So using this, we can also get this answer. Yes, I think somebody. Put, okay, sorry for this. I'll get back to you for this doubt. Yeah.
Are there the decision for some other course or what?
Sorry.
Means I cannot see that in the calendar. Maybe he.
No, I think no. There are 2 sessions that has been scheduled, but one has to be changed. I mean, one has to be basically removed. There is only 1 session, not 2 sessions happening on Saturdays. It need to be updated. Okay, so is this question clear to all of you? This centering of kernel matrix?
Clear, ma'am.
So basically, ma'am, there are 3 TA sessions, right?
No, there are 2 TA sessions.
No, ma'am, because there is actually in the calendar there are 4. One is on Thursday, and 3 are on Saturday.
3 are on Saturdays.
One is from 6 to 8, and 2 is from 8 to 10.
No, okay. Need to be removed.
So how many TA sessions actually?
There are 2 TA sessions each week.
Okay, ma'am.
Yeah.
Thank you.
Need to be removed. Yeah. Thank you.
Can you elaborate on this formula Kij? Okay, Kij is the
Yeah.
okay. I is
This formula.
the vector. I is the vector where one is in this
This one.
1j vector. 1j vector is the vector where
A vector, like at the ith element, you will have
there
the
is
1,
1.
and rest it is 0. You can think of
1
it
and
as
1, not 1 by n, it's 1.
1. It is 1.
Okay. And what is theta?
This theta is this. So if I fix any I, then I should get, I mean, let's say I fix I to be 1. Okay. So what should my theta 1 be? Look at this matrix. If I fix I to be 1, it means I will look at the first row, right? So what we are saying is for the first row, this is J. Okay, for the first row, add all the entries of the first row, and that. So once you add this, what should you get? You should get 2.3, and now 2 by 2.3 divided by 3, and that should be a 5-1. If I'm talking about the
5-1.
row. Yeah.
Okay.
So here I denotes your row and J denotes your column.
Okay. Yes, but that is the theta 1 is how much? Theta 1 is how much then in that case?
Theta 1 is coming out to be, I think, 0.76, right? This is the value that we are getting.
1 plus 0.8 plus 0.5 by 3.
So that is 2.3 divided by 3. So you solve for it and you should get 0.76.
Okay. And what is I P? P is
What? Yeah. So P is. So P is basically this is saying 1 upon n square times sum of all the entries of K. So this is the K that is given to us. Now I take all the entries of K, add it, and divide it by n square, which is divided by 1 by 9.
okay.
If you do all this, again, you should get the same set of matrices that you have gotten over here.
So this formula I think is important because in the exam we might be asked to calculate Kij only, not the entire matrix, no?
Okay, so this centering of the kernel matrix, I mean, yeah, this formula is given to you, and you should, I think more than this, doing it through this process is easier, is what I feel.
Suppose in the exam we are asked some ijth entry of that kernel matrix.
A centered kernel matrix, yeah. Then you should.
Then you have to use this formula, right? The one which.
Yeah.
Instead of calculating the entire matrix.
Everything, this is better. Yeah.
Yes.
Okay. So that was all the questions I had for today. For the Solve With Us session. Anything specific? Any doubt you have in these questions?
Formula.
Yes, Prakash.
Ma'am, formula, how it is coming, ma'am? Can you explain that formula once again, ma'am?
Which formula? This formula.
K minus K1.
Yeah, this one.
Yeah.
Okay. See. So we will use this basically.
That is also I have doubt. X-centered means that average value.
Let's think of it as let's take a small example. Okay.
Yeah.
So maybe my X is, write it here. So my X is, let's say 2, 0, 1, 1, 1, 1, 3, 2, maybe okay, 3, 0, minus 6. Yeah, let's take that. So this is my matrix X. Now, what we are saying here is you do for x centered, if I have to find xc, then it is, I will do this x minus x n cross n, this matrix, right? So basically this minus, okay, so this minus 2 1 3 0 1 0 1 1 minus 6 times the matrix 3 cross 3. And what is this matrix 3 cross 3? This matrix is 1 by 3, 1 1 1 1 1 1 1 1 1. Okay, so I solve for, let's see, let's solve this. So what do I get? I get, if I solve for this, I get first row, first column. So basically what you're doing is you are adding this, all this element, right? Because when you multiply each with the same number, it's going to give you the same number, right? And that's how you do the matrix multiplication. So 3, 4, 5, 6 you get. Now you do it for second one, you get again 6, you get again 6. For the second row, you will get only 1. Again you will get only 1, again you will get only 1. Then here you will get 1, 1, minus 6, which is minus 4.
Minus 4, yeah.
Minus 4, minus 4 is what you will get. So if I divide it by 3, what is it that we are getting? It is 2, 2 and 2. Okay. Then here
0.33.
0.33, 0.33, 0.33, and
1.33.
minus 1.33 minus 1.33 minus 1.33. Okay. Now if I take x and subtract this x from here, what should we get? We should get
0.
2 minus 2, which is 0. 1 minus 2, which is minus 1, and
1.
1 minus
3 minus 2.
3 minus 2 is, yeah. Okay. Then 0 minus
minus 0.33. 0.67.
yeah, 0.67 minus 0.33. Okay. Then what is? Then you have 1 minus, so it is 2.33, right? 2.33. Then you have 2.33 and minus 6 plus 1.33. This should be minus 4 times maybe 6x, something, 6, 7, let's say. This is what we get. Now, can you see that now they all are centered?
Yes,
Minus 1, 1, 0. This will be 0. This will be 0. They will be all 0. This will become center.
yes.
So now we will use the same technique to center our phi of x. So my K matrix, the kernel matrix, which was phi of x transpose phi of x. Okay. So this is my kernel matrix, and if I have to center, I have to first transform to phi of x and then center phi of x, right? So if I have to center phi of x, I will use the same thing. So I will use basically this. It's not written. So phi of x, if we have to center, let's denote as c, then it will be phi of x minus phi of x times this matrix, right? This is what we will do. So since this K is phi x transpose phi of x, and if we have to write it in the center term, I will write it as phi of x centered transpose phi of x centered. Okay, and each of these can be written in this way. Okay, and we solve for it. We just do the calculation, some algebra, and we get this as the final expression.
Thank you, ma'am.
Okay, any other doubt? There's nothing else? Okay. So that was all I had for today. Anyone has to discuss something? Or
Ma'am, can you give some idea about week 1, week 2, what we study about the it's a general uh, related to that, I mean, outline, can you say, ma'am? Week 1, week 2?
week 1, week 2.
Yeah.
Okay. So in week 1, basically week 1, week 2 is all what we are doing is the principal component analysis, right? And we started with like why are we doing the PCA and how are we performing it, right? So basically the idea was to compress your data set. So if you have data set which is in higher dimension, can we compress it to a lower dimension and get something useful from about the data set from there? So that is why we what we did is we took the projection of the data set onto the principal component, right? And those principal component, how did we obtain it? Those principal component or the principal direction is what we said is coming from like your covariance matrix ka eigenvector, the largest eigenvector, if I talk about the first principal component. So we projected our data set onto some line, right? Or you can start with like you have a data set, you identify, you have to find a line. Okay, you have to find a line. You don't know which line, you just have a data set. Now you have to find a line such that when you project it onto that line, you are able to compress it properly. I mean, and you are able to compress your data set, and that is giving you much information. I mean, enough information about this. So that direction, like what we saw, is found by this covariance matrix, largest eigenvalues, largest eigenvector, and that was the first principal component. So we projected it over there, and then whatever the proxies we got for those vectors, I mean those data set, we said that like okay, now before when we needed, let's say some like if you have data set in b cross n dimension, and then in that case we needed a much larger value to store a data set. When you compressed like when you projected it, we needed a lower dimension to store the whole data set. So that was one benefit that we got. And what we saw is that it's not just the first principal component. So depending on like what's the dimension, depending on that, we kept on projecting it onto like residues and so on, right? And we had gotten some nice relations between the data point and our vectors. I mean, xi, wi's. all that we had seen. So week one was mostly to introduce what the idea of the projection was, or what the idea of the PCA is, and how can we compute it. Then, and then what we also saw is the variance, like the first principal component was along the largest, along the eigenvector, which is, okay, so what we saw is the variance is given by the largest eigenvalue. So the first principal component, you have the maximum variance. So that is another result also that we had seen. So these were the major topics in week one. Then when we moved to week two, we saw some issues with the PCA that we had to take care of. Like in cases where your data set dimension was quite large, so it takes quite a lot time to like the complexity, the time complexity was quite high. In that case, we came up with this method of like XA, like we are doing the kernel matrix. Okay, not the kernel matrix is later. Before that, we have to okay, what we saw first. What we call it maybe. Okay, yeah, okay. So in week two, we started with the two issues of the PC, right? The very first issue was the time complexity issues, and the second was the structural issue. So in the time complexity issue, what we saw is that to find, I mean, if we have a data set which is in very high dimension, then in that case, to find this, to compute this eigenvector for the covariance matrix W, we need, we were able to write it as in the form of x times some alpha, some alpha k vector, which is in n cross one dimension. Now those alpha k's are constant for us, and those alpha k's can be computed by finding the eigenvector and the eigenvalues of the x transpose x matrix, right? So we did not have when you have to find this W, this principal component, which is given by W, you can, instead of finding the eigenvector eigenvalue for the matrix XX transpose, which is the covariance matrix, you find it for the matrix X transpose X. And that we, what we got is that this is given by X is equal, or W is equal to X times beta K divided by under root of n lambda K. The beta K was eigenvector of X transpose X, and n lambda K is eigenvalue of that matrix X transpose X, assuming that all these eigenvalues are positive. So this is how we dealt, I mean, we saw all the mathematics behind it. And from there, we saw like if you have a higher dimension, then this is the way we can find RW, the principal component where we have to project our data set. Now, from like doing this, like we were able to reduce the complexity from order of D cube to order of N cube. So this is good. And this is how we can work with it. And the next issue that we had seen was what if the structure in the data set is not linear, then how do we deal with it? So the structure is, the data set is not linear, then in that case, we went for the kernel PCA, where what we are doing is we are first transforming our data set into a higher dimension, and we are performing our PCA in that dimension, basically in the higher dimension. And doing this, to do this kernel PCA, we needed the kernel function. And what we also saw is that there are some kernel function which are all right. So to do the kernel PCA, you need the kernel mapping, right? You need the mapping, and for that mapping, to explicitly know that mapping, the alternative way or the alternative way is that you use this kernel functions some valid kernel, which can be written in the form of phi x transpose phi x. So use that to find the eigenvectors or the eigenvalues. Basically, all the process will stay the same, whatever you have done for standard PCA. It's just whatever you were doing for x transpose x, now you will do here for phi x transpose phi of x. And those phi x transpose phi of x, you will get using this kernel mapping that will define. That we have seen. And here, like once in the kernel PCA, what we had also observed that once you can do all this, but the explicit WK, the eigendirection, is something which we won't be able to find it, right? But what we will be able to find is the projected data point that we were able to find it over here. And yeah, I think overall this is what we had seen in week 1 and 2.
Thank you, ma'am. Ma'am, the eigenvalues are 3 eigenvalues. The dimension of the reduced dimension of the data is it a number of eigenvalues? The reduced dimension of the data, given data, is it a number of eigenvalues?
No. That
No.
is not, no.
Principal components, is it a number of principal?
Those are the representatives, right? So like when you started this week 1, we started with very simple examples where, let's say, yeah,
yes,
yeah, those are representatives, and you find the coefficient and product of coefficient and representatives is what can reconstruct your point. Okay, now anything else? But then let's close the session for today. We'll meet again tomorrow for week 3.
Thank you, ma'am.
Yeah, thank you, everyone.